Hi there, guys. It's just me, Mr. Wee. I'm here to kind of go over some other problems that we had from your exams and so forth for test corrections and for problems I think will be helpful for you to know. So here, this is actually number 17, multiple choice question number 17 on month 5, on your month 5 exam. So we're going to be taking a look at this. So why don't you take a second, you can pause this if you want to read to yourself. Population P grows according to the equation dP dt equals Kp. Okay, so dP over dt tells you that there's a rate of change. All right, dP over dt is equal to Kp. That's some constant K is equal to P, where K is a constant and T is measured in years. Okay, if the population doubles every 12 years, then the value of K is approximately. So here's some keys here. You have dP over dt is equal to K times P. This problem we really didn't go over as much in class as we did extensively derivatives and integrals, but it's a problem that might come up. I would say probably out of 20 multiple choice questions, you still have a 1 in 20 chance of seeing this. So there might be at least one question that looks like this. So let me kind of show you guys what you guys are going to do now. So let's have a look here. If I can kind of move this here. All right, it's a little bit of a delay. Okay. So here's the situation. We have, after t equals 12 years, okay, that's 12 years, your population doubles every 12 years. And then we were also given this, dP over dt is equal to K times P. And what we're essentially solving for is K. Now, this looks simple, but it's actually really not in terms of what this implies. So if you see something like this, and you see something about a population doubling, or maybe decaying, or there's a half-life every something years, so at a rate of every few years, the population doubles or decays, this is going to be a growth in rate problem, or growth or decay rate problem. So this next step takes a little bit of a leap of faith, okay? This is something that you got to memorize. We will need a proof in between this step going from here all the way to here, because what this will imply. So in part 2, I'm going to show you the proof for this, right? But you can kind of go back in your previous chapter. It has to do with growth and decay. So look in your AP calculus book for growth and decay, okay, that section, and you will see the proof for this. And I will go through the proof in the next video. So here's what you're supposed to do. You're supposed to go from here. So it's some constant times P, the population. This is the population. And then this is the rate. So what we're going to do is we're going to kind of do the antiderivative of this. And what we're going to end up is something like this. Your new population, this is new population. Hopefully this kind of sounds familiar. This is your new population, your overall, or your final population. This is final population. Okay, that says final. That's final. I know that doesn't look like it. It says like, it looks like fine, but that's final. That's my weird writing. Population is equal to your initial population times E to the K times T. So if you look in your book, if you remember what this means, this simply means that your new population, okay, whatever it is going to be your initial, whatever your initial population was, times what I call, this whole thing is either the rate of decay or growth. Okay, that is the rate of decay or growth. This whole E times K to the T part. That T is where you put in the time, okay? And K is that constant that we're solving for. So we just got to figure out what things we're going to plug in. So I'll tell you this, the T times 12, we're definitely going to put in here at some point, but it's just, what do I put in here? I don't know what my initial population is. And I don't know what my final is. So that's a little tricky. So how do we set this up to figure out T? So again, going from here, we're basically taking the antiderivative of this to get to here. I will show you how to do this proof, but on your exam, this is pretty much what you want to do. You don't want to go through the proof and try to figure this out and get to this, because that would be part 1 of like a 2-part long answer. You just want to go from here and quickly memorize, or you want to have memorized that it goes to this. If you have something that talks about time, population doubling or decaying, okay, doubling, tripling, or it's mainly just doubling or being halved, okay, decaying by half, and you're given the derivative dp over dt is equal to k times p, some constant times the population, the initial population, or the initial amount that you have, you should know to go here right away, okay? Which is the new amount is equal to the initial amount times this rate of either growth or decay, okay? So anyways, let's continue on with what we're supposed to do. So basically, this is what you have. Your new population is basically 2 times as big as the initial population. That's pretty much it. What, Mr. Wee? What are you saying? Okay, so basically this, you're going to set this equal up to p of 0 times e to the kt. So basically the population is going to be twice as much. So the new population is going to be twice as much as the old population. So what is it that's important, or why did I say that? Because you're setting this equal to this, and basically what I'm trying to say is, if and you can kind of do this mathematically by like dividing both sides by PO, but you don't need to. You can just see right now what I'm trying to say is that 2 is equal to E KT. That means the growth, or the rate of growth, will be 2 is equal to 2, because we know that it doubled, okay? So we're going to set this whole thing up. This is the rate of growth and decay, or basically how much it grew or decayed, okay? How much did your population grow or decay? Well, we know that it doubled. It went up by a whole, uh, uh, basically twice as much, okay? I was going to say by 200%, but that would confuse you. It's basically going up twice as big. So you set 2 equal to e to the kt. But if you want to do it mathematically, you just don't see it. You can divide both sides by the initial population, p of 0, and basically you're still left with this. Okay? 2 is equal to e to the kt, and then you know the time it took to double is 12 years. So you plug in 12 there. And then that's it. You just basically solve for k at that point. So again, let's kind of, if you want to kind of visualize it again, you can just look at it like this. So on the exam, the way you set it up is like e to the kt, right? E to the kt, and then you just realize that's the new population, and then basically we're taking the old population, we're doubling it. So basically you could just do this by eye. Oh, if we're doubling it, we'll just set this equal to e to the kt is equal to 2. So you don't have to do what I did here. If that confuses you, if it just makes more sense to look at it and be like, that's the new population, that's the initial population, I know that I'm going to double this. So basically doubling it means this is going to be equal to 2. If that doesn't work, then you go with this method. You have to visualize it as P is basically my new population is twice as much as my initial population. And then I also know that you have to set that up equal to P0 of times e to the kt, and then basically you divide both sides by p of 0, and then you have the same situation. 2 is equal to e of k times t, but in this case we know that t is 12, and over here is the same thing. e to the k times t, which is 12 years in our problem. Okay, so let's just solve this. Okay, so let's solve this. Let me rewrite that. It's 2 times e to the k, or 12k basically. Okay, so I have 12k, and I want to get rid of this e, so I'm going to take the natural log of both the sides. So I have natural log of 2 now is equal to basically the natural log, and that e will cancel out, giving me 12k. And then I just divide both sides by 12. Okay, and basically I have k is equal to ln of 2, which has an actual value if you plug it in your calculator, over 12. And then let's see what we get. Let's go back to, let's go back to the problem here. So those are my, let's see, sorry. Those are my possible choices that you see right now. I'm going to go on my handy dandy calculator. So this is a calculator OK problem. So here, whoops, sorry. If I can turn down the brightness maybe. See if I can get that Can you guys, oh, no, can you guys see that? Maybe it's a little bit too bright. Okay, so let's go to my graphing calculator, which looks a lot like your calculator. Okay, this is a program that costs about $10 online, but I'm a little bit older than you guys. I have my own credit card and stuff, so I can buy this. But just do this on your TA83. This models itself after the TA83, basically. So you're going to put ln of, so the ln button, where's the ln? Oh boy, I definitely feel old. Okay, so there's ln. ln of 2 divided by 12. That is, let's see, that should be ln of 2 times 12. That's 0.0577. Okay. And if we go back to our choices here, looks like E is our final answer, and that is the correct answer. Okay. All right, guys, I'm going to stop right here. And then in part 2 of this problem, I'm going to go through the proof for why that is. Okay. Thank you guys very much. You guys have a great night. Bye.